So chi-squared, that is the symbol. That's the Greek letter for chi. It looks like an italicized X, but it's almost like a capital italicized X, and then of course the square notation. Today, you guys are going to determine whether or not data sets are dependent on one another. In other words, you basically are trying to you use this test to basically see if certain data sets are independent of each other, meaning they have no effect on the outcome. Okay? And so basically how we're going to do this is we're going to basically take an example, and it's going to be like an ongoing example to walk you through the steps of how to perform the chi-square test. Okay? Are we ready? So the purpose of like I said, the purpose of the chi-square test is to, again, you use it to determine whether or not two sets of data are independent, okay? Whether two sets of data are independent of each other. There are four main steps to perform the chi-square test. There are four main steps. Now realize, and I'll point this out, on examinations, on tests and things like that, you're going to be using 3 out of the 4 steps. But again, if you decide to do a chi-square test, a part of your IA, then you'll end up doing all 4 tests, or all 4 steps, okay? So here's the example that we're going to use. It says, suppose you collect data on your favorite color of t-shirt for men and women. You may want to find out whether color and gender are independent or not, okay? So, some people say, well, girls like pink and yellow and lavender and stuff like that, and guys are more of like black and blue, those solid man colors, whatever. Okay, you can run a test to see if that really is true. Like your gender is a preference of color. Okay, so this is the example that we're using to perform all 4 steps. We ready? Let's do this. Step 1. You always want to write your null hypothesis and your alternative hypothesis. The symbol H sub 0, and that is a 0, that's not an O, represents null. And H sub 1 represents your alternative hypothesis. And the null hypothesis basically states that the data sets are independent. The alternative hypothesis states that the data sets are not independent. For tests, you probably will have to write both. But if you're doing like your IA project and decided to test whether or not these 2 things have anything to do with each other, you just only have to write your null hypothesis, okay? Because clearly the alternate is the opposite, so it's just a part of it. And now we're going to actually perform the test that's going to either confirm that hypothesis or reject the hypothesis, okay? Almost like a science experiment, okay? What would be our null hypothesis for this particular example? Talking about, that ongoing example. What would you say would be our null hypothesis? Say that one more time.
Preference of t-shirt color is not dependent on gender.
Careful. Null actually states that they are. You said not. Okay, right there. I want to make sure that we cut it right here. Don't say that. Say independent. Don't say not dependent. Okay? Because when you do that, when it comes down to actually determining whether you accept or reject that null hypothesis, like you end up kind of contradicting yourself, and it's almost like you got to do the opposite of what the rule is. So just say independent, right? Because that's what not dependent means, right? Independent. Okay, so there we go. Like you said, preference of color is independent of gender. I'm going to shorthand that. I'm just going to say color is independent. But yes, that's exactly what you would write. So then the alternative hypothesis is what? Color is not independent. You know how there's always like those few, gimme points in certain problems? These are the gimme points in these types of problems, okay? Yes, I'm dead serious. But so many students, they use other words to mean independent, okay? And then that's when that's when the issue starts, and it's just downhill from there, okay? So it's pretty much the same format. Blank is independent of blank. For the null, blank is not independent of blank. for the alternative.
What do you put just
Why would you just put just dependent? Because like I said, once you actually get through the whole process and you actually have to state whether you're going to accept or reject, depending on what you said, is actually going to be the opposite of that. If you want to use dependent, which ended up happening with my seniors and they're still using it and they're still getting it wrong, then by all means, go ahead, okay? But I'm trying to help y'all out. I know what could happen. I'm trying to prevent that from happening, okay? But at the end of the day, y'all gonna do your thing, and I can't stop you, all right? So, step 2 is the actual process of calculating the chi-square test statistic. This is where the work is in the chi-square test, okay? The first thing you need to do is you need to put your data into a contingency table, which shows the frequencies of your two variables, right? So this is basically where you put all your data into a nice clean table, okay? How many guys like black shirts, or how many girls like red shirts, and so on and so forth. This is where you actually make your table, okay? Again, this is what you observe. This is your actual data. And the elements should be frequencies, not percentages, okay? Not that 25% of guys like blue shirts. No. It's how many of those guys like blue shirts. It's always frequencies inside of your contingency table. Thank you. I got the word just that fast. Okay? A lot of times, this will be given to you on tests and things like that. When you create your own, that's when you actually have to go through that process. So for this example, I give you the contingency table. As we can see, there are 48 guys who like black shirts, 46 females who like white shirts, 27 females who like blue shirts, and then their respective totals. How many people did they interview to figure this out? 300. Now, from this observed data, you can calculate the expected frequencies using the formula for probability of independent events. The probability of A times the probability of B. Now, you do need to know how to determine this, okay? Will the test question ask you to find all of the expected frequencies? No. They might only ask you to find one, but you do need to know how to find it. It's a very simple process, okay? Probability, a part divided by the whole, okay? So when it says the expected number of men who like black t-shirts, okay? What you do is, wrong way. What you do is you take, okay, there's 83 total who like black shirts. No, like total who like black shirts. There are 150 total guys, okay? What you do is you take those two numbers, you multiply them together, and divide them by the total amount that you have. So it's that respective row total and that respective column total. You multiply them together and then divide by your total amount. Yes?
So when okay, that's confusing though, because like if you use that same number, you get the same. Because you're using the total of all the black shirts, you get the same number for both male and female.
Yes.
But there's more males that like black shirts.
Right, but we're not finding the probability of a guy liking a black shirt. We're finding the expected frequencies. To find the expected frequencies, you basically are using the whole independent events concept, which we'll go into more detail once we get to probability.
So when it says expected number of men who like black t-shirts, it's meaning the frequency of.
It's meaning that you're basically taking, okay, you have this many people who like black shirts, you have this many males, you're going to multiply them together and then divide by 300. And that's going to give you the expected number of guys who actually like that particular color.
Wouldn't that same concept be applicable to the females because you're just taking the total and not so?
The only time that they'll be different is when you have different totals when it comes to like, say they only interviewed 100 females instead of 150. That's when like that number will be different. Okay? What is this number? What is 83 times 150 divided by 300? 41.5. Okay?
41 or 40? 41.
It's 41.5 what?
Just 5.
Oh, it is just 5? Then it's just that. 3 significant figures. We'll still use 3 significant figures here.
Like from men, that's weird.
Yeah.
You don't have to have
This one, because we're using this to get our final answer, it's the whole premature rounding thing we don't want to do. Okay? Let's continue. Number of men who like white t-shirts. What are going to be the two numbers that we multiply together? 58 and 150, and we're going to divide it by 300. Even?
Yes.
No decimal?
No.
Cool. Expected number of men who like red t-shirts. 75 times 150 over 300.
37.5. P and then parenthesis A parenthesis multiplied by P parenthesis B parenthesis.
What's the last two numbers that are multiplying together?
84 times 150.
One more time.
84 times 150. And you get 42.
Straight. Okay. All right. That's how you figure out those expected values. Okay? Or the expected number. Yes, they'll end up being the same for the men and women because they have the same totals. Okay? So that is what's going to go into our expected frequency table. 41.5,
29.
29,
37.5.
37.5,
And 42.
and 42. Again, these numbers won't always be the same. The reason they are the same is because the totals for the males and the females were the same. Okay? Expected values can never be less than 1. That is major. Okay? If an expected value is less than 1, which will never be for your test, but let's say for a project or for your IA, that means that you need to condense 2 columns. Okay, so then that way you won't have that. You'll end up running into inaccurate results that way.
So like what's an example of something that could be less than 1? Like
Let's say our raw data, like say like the number of guys who like blue shirts was really only like 2 instead of the number that it was. You know, something like that can cause one of your values to end up being less than 1. And so in those cases, you would need to condense the blue column with the red column. And then it'll just be guys who like red or blue shirts.
oh okay.
So it's almost like when you don't have enough data,
You have to merge it.
then you have to merge it with another one.
Oh, okay.
Now the formula to calculate the chi-square value is the following. You take your observed frequency, you subtract it from its corresponding expected frequency, you square it, and then you divide it by the respective expected frequency. And you do that for every single entry and add them up. Okay? So that's what we're going to do. We're going to find the chi-squared value by using this formula. There is a, yes.
Are you recording?
All right, so we have to take every respective observed frequency and subtract it from its expected, okay? So, the first column was black shirts and men. What was that number?
81.5.
No, what was the observed one?
48.
There were 48 guys who preferred a black shirt. We're going to subtract that from its expected frequency, which was 41.5. We're going to divide that by 41.5, and then I can't forget, I got to square the numerator. Okay? And then I'm going to do that same process. Now, the next color was guys who liked white shirts. How many guys like white shirts? 12 guys like white shirts. I'm going to subtract it from that respective frequency, which was 29. I'm going to square it and then divide it by 29. And I'm going to continue to repeat that process. What's the next one?
33.
And the last one for the guys?
57 minus 42.
We're adding all of these.
We're going to add all of these, and we got to do the same thing for the women. Okay? Now, do realize the bigger the expected and the observed frequency tables are, the more you're gonna have to do when you do it by hand. Okay, so that is something to keep in mind if you ever have to create one yourself.
In this case, we just double the answer for the.
No, because remember we don't have 48 women that like black shirts, so those numbers are going to differ. How many women like black shirts?
35.
So I'm gonna do 35 minus 41.5, square it, and divide it by 41.5.
When you do all of that in the same.
Yeah, I mean, of course you can do them individually and then add them up all together, but you know, to save space for what we have right now in our foldable. What about white shirts for women?
46.
I don't know why that many women like white shirts because, you know, the staining. You can't stand it. And they're see-through. What's the next color?
42.
42 red. So I have 42 minus 37.5 squared over 37.5 plus 27, who like the last color, and divide that by minus that from 42. That is the math that goes along with it. If this were an IA, this is what we would have to show. And then we can go to our calculator and type all this in to actually get our number. So I'm going to give you guys a few moments to do that. And let's see if we get the same value. And your answer is 33.8. That is your chi-squared test statistic. Okay? Now if you try to type it in, you didn't get 33.8, you know, just go back through and then take your time, you know, for homework tonight. But will you be expected to do this by hand? No, not for a test. As you can see, it took us a pretty long time. But you do need to know how to do it in your calculator. So flip your page. What does this mean?
Yeah, 33.8. What does that mean?
The 33.8 is a particular value that you have to compare against another value. That's a part of step 3 and then step 4. So that number is actually compared against another value, and if it's greater than that value, then you're either going to accept or reject the null hypothesis. It just depends. So basically, that number is used for a comparison. But how you do it on your graphing calculator, you see how you have that little bit of space? It's to write down, you know, the steps, okay? So what you do is you have to press your second button, and then you have to press your x to the -1 button. When you do that, it takes you to your matrix, okay? Now, if you've never used matrices before, then yours should be blank. If yours already has something beside them, don't worry about it because we're going to change it. But this is where you have to go, and you have to go over to edit, okay? Because edit allows us to fix our matrices. Now, when you click enter on edit, it's basically like a table. What we have to do is we need to type in our observed data. And what we do is we use the raw data. We don't include none of the titles or none of the totals. Let me finish this off real quick. You don't use none of the titles or none of the totals, okay? So what size would that matrix be? How many rows does that matrix have?
1 by 1.
No.
Wait, you talking about in our 2 thing?
I'm making
It would be a 2 by 4, okay?
I didn't know you meant in thing.
Look at your observed. It's this data right here. There are 2 rows, and then there are 4 columns.
2 by 4.
2 by 4.
So it's going to be a 2, enter, 4, enter. And it basically will form those spaces.
Oh, that's really cool.
And what you do is you actually type in your data just like how it appears in the table. So you'll type in 48, you'll type in 12, 33, and 57 for the first row. And basically after every entry, I'm pressing enter. 35, 46, 42,
27.
and 27. Okay? Now once you get all your data in there, you got to quit out of the program.
Like second quit.
Yes. So second mode to quit out of the program. If you try to do anything at this point, you're going to end up like overwriting the matrix. Now let's get our chi-squared value. What you do is you go to stat, you go over to test, and you want to scroll up or scroll down to option C, which says chi-squared test. Go down where it's set to C.
Is it x squared? Okay. Whoa.
Yeah.
Okay? Now when you click enter, everybody should have the screen. Doesn't matter what calculator you have.
Wait, stat? Wait,
Was
what?
it X? The color doesn't
the color doesn't matter. Clearly, mine's a more updated one, but yours should at least say observed A, expected B,
Where
calculated.
do we go from stat? Okay.
Over to test, and then you go to option C. Now, our observed data, our raw data, we type that in A, correct?
I have an option.
It will always format this way as long as you type it in A. Okay? Always type your observed in A. And what you do is you just go down to calculate. Don't worry about the color. To be honest, I really don't know what the color does. Okay? Go down to calculate, and when you click enter, 33.8, right?
That was so fast. Wow.
33.8.
What?
Wait, so for the second,
I'm
for B,
mind
you
baffled.
entered the expected.
Yeah.
See, the thing is that with the calculator, we don't have to enter the expected table. Now, if you actually go back to your matrix and you go over to, you see that? Remember, I didn't have anything in B. What the calculator does is it actually goes in matrix B. Weren't those our expected values? So in your calculator, it does it for you. Okay? Now we'll talk about the rest of the steps, step 3 and step 4, next class. Okay? But your homework tonight is to start working on the correlation coefficient for your project data.
Yes. Wait,
All right.